I have another physics problem for you. So let's have a look at it. Well, this is a cylinder. It's filled with air, and this is a piston. So this right here is in its equilibrium position as given. So the pressure here will be the same as here. Now, this is a pretty simple problem, but we are going to look beyond the formulas at the math where the true physics lies. So when we are given a problem like this in oscillations, we obviously displace the mass, which is gonna oscillate like this. So I'm gonna summon Boyle's law now, because we need the pressure and the length, which comes from volume. So P1 V1 is equal to P2 V2. That's Boyle's law. It only applies if the temperature is constant. So let's substitute the values. This I'm taking as A, and the original length is L. So this is A and this is L, the volume. Now P2 is after we displace the mass. It's P dash. We need this pressure, and A, which is the area, plus the new length, which is the displaced length. So this is gonna be L plus X. Now you will notice that the areas cancel, and we find that the pressure after displacing is this. So now we have this. The pressure inside the cylinder is less than the atmospheric pressure because we have stretched the piston. Now, because there is an imbalance of pressure, there is more force over here than here. So now let's think about the forces. So force is just pressure into area. This area is the piston's area. When we find the net force, it's P naught A minus P dash A, because P naught is greater than P dash. So this comes out to be P naught minus P naught L plus X into area, right? Now this is not SHM. I mean, the force for SHM, the force should be proportional to the displacement, right? And this is not. So now this is where the interesting part lies. Let's graph it in Desmos and see what kind of a graph it makes. So this is the graph, this is the equation, and these are some random values which is irrelevant to this problem. Now if you observe this graph carefully, you can see that this graph is eerily similar to the stress strain curve of a solid, as you can see. Isn't it crazy? It looks exactly like the stress strain graph of a solid. It means that we can use Hooke's law on a question which is about gases. it's crazy. So, and granted, it's only valid for small oscillations, as we will see. So let me mathematically prove it to you. So if we just simplify this, it's I'm taking P naught common, P naught and area, so it's 1 minus L plus X, which is P naught A L plus X minus L plus X, which is P naught A, which is P naught A X L plus X. Now since the oscillation is very small, it's smaller than L, we can just neglect this, right? So this is the new equation. The force is proportional to X. Hooke's law. This whole thing is the Hooke's constant K. I mean, I'm not saying that this is Hooke's law. I'm just saying that we are using something similar to Hooke's law here. The force is proportional to X, as we can see here. So this indeed is SHM, and we can see that it's a pretty accurate approximation, neglecting the x part over here. It's pretty accurate. I mean, if we change the values over here, it pretty much follows the original graph for very small oscillations, of course, as you can see. I mean, this curve comes because of the fact that practically solids are compressible and gases are also compressible. So, I mean, there was bound to be some kind of similarity between the graphs, but it's still pretty cool. So this is the answer for the original question, by the way.